Good day and welcome back for the fourth part of our discussion on integrating rational functions. And just to provide a quick recap, in our previous discussions we've reminded ourselves of this algebraic technique known as a partial fraction decomposition. A partial fraction decomposition allows us to take a rational function and algebraically rewrite it as a sum of simpler pieces that we can more easily integrate. So with that in mind, we should really think of a partial fraction decomposition as being a very positive thing, something that we are even excited to do because it's going to turn the integral into a much easier problem once we get that algebra out of the way. In this video, we're going to focus in on one example showing a slightly more involved partial fraction decomposition. I usually tell students as we're going over this in class, if you can follow through and understand how we do this partial fraction decomposition, I'm fairly confident that you can do most PFDs that we encounter. So in this case, to get us started, the denominator is degree 5, the numerator is degree 3. It's a proper rational function. You have a single linear term and a repeated irreducible quadratic. What I would like you to do is pause the video and write down the form of the partial fraction decomposition. And based upon how the denominator is factored, we see immediately that the PFD will contain three terms: a linear term, and then two terms corresponding to each of the factors of x squared plus 4 quantity squared. We balance out a term from a linear piece with a single constant, and from an irreducible quadratic we need two constants. So bx plus c and dx plus e. Once we've written out the form of the partial fraction decomposition, we need to solve for these constants a through e. But algebraically our technique is always going to be the same. We start off by clearing fractions. So take the denominator on the left and multiply each and every term by it. On the left-hand side, you're left simply with the cubic polynomial in the numerator. In the first term on the right, the x minus 1's cancel. In the middle term on the right, an x squared plus 4 cancels. So we have the bx plus c in the top, x minus 1, and a single x squared plus 4. And in the third term on the right, both of the x squared plus 4 terms cancel, and we have dx plus e multiplied by x minus 1. And this is typically what we expect to see. It's going to look a bit messy at first, but recall, for any linear term, there should be an intelligent choice of x that we can substitute in to immediately solve for that corresponding constant. In this case, note, if x is equal to 1, the middle term and the third term on the right-hand side vanish, and that will allow us to solve for a. So I usually just do this kind of to the side, but if we substitute in x equals 1, on the left we would have 1 plus 10 plus 3 plus 36, which is 50. And on the right-hand side, the only term that doesn't vanish is a times 5 squared. So immediately, we've determined that a is 2. And determining this value of a before proceeding further is going to save us quite a bit of time and grief later on in the problem. So now that we've determined any constants that we are able to by using intelligent choices of x, our next step is to take the right-hand side and expand everything out and group together corresponding powers of x. And instead of going through each and every individual step of algebra, which we certainly could do, I'm going to put a ... and I'm going to let you fill in a few details. But in this case, when you group everything together, you'll have an a plus b times x to the fourth, a c minus b x cubed, then the next term is 8a plus 4b minus c plus d, all times x squared, plus minus 4b plus 4c minus d plus e times x, and then the final constant term is 16a minus 4c minus e. And it's quite possible that expanding everything out and grouping together the terms could be the most difficult part of this problem. And I'm going to copy down this cubic on the left as well. And recall, what we have is a polynomial equal to a polynomial. And the only way two polynomials can be equal to each other is if each and every coefficient is identical. And to make this look a bit more similar, on the left-hand side, I'm going to go ahead and note that there's really a 0x to the fourth, and how about we'll throw a 1 in front of that x cubed. Now, equating our terms, we can see that the coefficient of x to the fourth on the right has to equal the coefficient of x to the fourth on the left. That is, a plus b is equal to 0. And because we already know the value of a is 2, we immediately also know the value of b. It is minus 2. And this is the point where we clearly see how helpful it is that we had determined a immediately. Now moving on to the coefficients of x cubed. C minus b is equal to 1. And because we know b is equal to minus 2, that tells us that c must be equal to minus 1. So as we go along, if we're able to solve for a constant, we go ahead and do so with the hope that it might help us in the next step. Now we go to the coefficients of x squared. Those need to be equal to each other. So in this case, we have 8a plus 4b minus c plus d equals 10. And because we know a, b, and c, we can solve for d. And I'm not going to try to do this all in my head. Let's instead write out a few details. A is 2, b is minus 2, c is minus 1. So we have 16 minus 8 plus 1. And those three terms combine together to be a positive 9, which tells us that d is forced to be 1. And we are almost there. We've determined a, b, c, and d. All that remains is e. So note, we only need to write down one more equation to work with, and I believe the constant term is the easiest of those equations. So equating the constant coefficients, we'll say 36 on the left is 16a minus 4c minus e on the right. And this once again kind of substitute in a few values. We already know that a is 2, and we know that c is minus 1. (32 plus 4 gives us a 36, and 36 minus e equals 36 is only possible if e is equal to 0. And now that we've finished the algebraic part of this partial fraction decomposition, let's go ahead and write out the form of our PFD, including those constants. Our rational function is equal to a over x minus 1 plus bx plus c all over x squared plus 4. And I'm going to immediately break that up into two fractions. So we have plus bx over x squared plus 4 plus c divided by x squared plus 4. and c is minus 1. And then finally we have dx over x squared plus 4 quantity squared. D is 1, so it's x over x squared plus 4 quantity squared. And e is 0, so that completes our partial fraction decomposition. Now note, this isn't the final solution. It's the majority of the work, I think the most difficult part of the work, but what we've been asked to determine in this problem is to evaluate the indefinite integral. So our final step is now going to be to integrate each and every term individually. So if I would like to anti-differentiate, we could break this up into 4 separate antiderivatives. And then evaluate each one individually. So just working our way from left to right. We would have 2 natural log absolute value x minus 1. Pulling the minus out of the integral, note, with the substitution u equals x squared plus 4, the 2x dx in the top is precisely du. So this would be the natural log of the absolute value of x squared plus 4. And if you don't quite see that, don't hesitate to include an extra step. The next part, pull out the minus, and it's a common formula. And recall that common formula, 1 over x squared plus a squared, is 1 over a arctangent x over a. And in fact, we evaluated this exact integral in a previous example. A is 2. And for the final piece, we would use that same substitution we used earlier. And note the only difference is now that x dx is going to be 1/2 du. So we will have an extra 1/2 out front, and the antiderivative of 1 over u squared is minus 1 over u. So once again, I'm leaving out a few small steps, but evaluating these integrals with a substitution is by no means the crux of this problem. And finally, we finish up by simply putting a plus c. And just to remind you of my comment from earlier on, this is a very involved partial fraction decomposition, and I would consider this a difficult problem. If you can work through each individual step, understand how we've approached this PFD and this integral, you should be good to go when it comes to PFDs for proper rational functions and integrating. But I am going to throw one other small comment in. We lucked out, in a sense, to have e equals 0. Let me just throw an additional question in here, which is as follows. When e is not 0, we would have to end up integrating a term of the form 1 over x squared plus 4 quantity squared. How would we go about evaluating that integral? Hint, it was a recent technique of integration that we've discussed. The x squared plus 4 expression in the denominator indicates that we could use a trig substitution. So we could evaluate this using the trig substitution, x equals 2 tangent theta. So that completes our current example in this video. What remains is for us to do even more practice. So I would strongly encourage you to go to suggested problems, but you can also find an associated class worksheet on Canvas. And before you view the next video, make sure to invest a significant amount of time working through some of the problems on the worksheet. We will summarize a few of them in the next video, and you can also find those full solutions posted on Canvas. Stay tuned. Take care.